Alright, this week let's talk about vector spaces, span, and linear independence. Suppose we have a vector and it's in this space. Well, it has some direction, so it might be pointing in a certain way. It has some size. There's a negative version, positive. And where can you go using this vector? Well, if you go forward or backwards far enough, you span the entire line. Alright, and as our vector changes, so does this line. Alright, so now maybe we introduce a second vector. Let's introduce this yellow vector here. Of course, it also moves around. It has a certain direction and a certain size. Now, on its own, it spans its own line. But depending on where this line points, we might get a much larger span. You see, right now, these two vectors are linearly independent because they span separate lines. But if our second vector were pointing somewhere else, the two lines might collide. In that instance, when the two vectors are in the same line, they are linearly dependent. You don't really need the second yellow vector, because you can already travel the line with just a red vector. Well, what happens when our second vector is pointing out of the first vector's line? The two vectors form an entire plane. Alright, an entire plane. Now, can we span the entire plane if both of the vectors are pointing in the same line? Well, let's find out. Here, we're letting the second vector move around, and there we see. When the two lines intersect there, when they're part of the same line, that plane disappears. The span is only a one-dimensional line right there. Alright, so the most we can span with two lines is an entire plane. What if we introduce a third vector? Now let's consider a blue vector. Okay. This one can also move around. It can be in that plane, or above it, or below it. And it has some length. There's a negative version moving around, positive version. Alright, so maybe that's a little confusing there, so we'll do this. And like so. As it currently stands, this third vector is linearly independent amongst the previous two. That is, all three vectors together are linearly independent. Well, how could this vector point to become dependent? Well, what if the third vector were inside that plane made by the first two? Right about there. Well, that third vector would be sitting inside the span of the first two, and so it would be linearly dependent. As such, the total span with all three vectors is still only that orange plane. But as long as the third vector points anywhere outside of that plane, we increase the span to 3 dimensions. Yes, on its own, the third vector spans a line, and with any of the other two vectors, we get a plane. We see the purple plane made by red and blue, and we see the green plane made by red and yellow. As long as these planes don't overlap completely, we get a three-dimensional space. And so we check what happens. Right now, we see we can currently get all three dimensions, but what if I start to change this blue vector? Well, we see there's a point where they completely overlap. And so now we verify that despite having three vectors, we only get a two-dimensional span. But as soon as that first vector pops out from the span of the first two, we get all three dimensions again. And so you see, span and linear independence are very closely related. To recap, if we only have one vector, its span is a line. Well, that is assuming that the vector is non-zero. Because as soon as the vector is 0, the span is nothing. It's just the zero vector space. As long as the first vector is non-zero, we span an entire line. Introducing a second vector, as long as it's not pointing within the span of the first vector, as long as it's pointing anywhere outside of that line, we span an entire plane. Alright, now how about the third vector? For our third vector, we can span all of R3, or all of three-dimensional space, as long as this third vector is somewhere outside of that orange plane. When the third vector is inside that plane, it's dependent on the first two vectors, and so we don't increase our span. We can see this by including the purple plane, or the green plane, formed by blue and yellow, or the purple plane by blue and red. But as long as the blue vector is pointing anywhere outside of that orange plane, we span all of three dimensions. Thank you for checking out this week's video. I'll catch you next time.